To solve this equation, we think about what x could be to get this value 3. Absolute value is distance from 0, so it could be that x itself is 3, because if you plug 3 back into this equation, you get 3. But it could also be that x equals negative 3, because if we plug negative 3 back into this equation, the absolute value of negative 3 is 3. So both of these solutions work. To solve this equation, absolute x plus 7 equals 10, we again have to consider what's happening inside the absolute value, because it could be that the absolute value, x plus 7, has the value 10, and when does that occur? And we can solve this simple equation using the properties of equality. By the subtraction property of equality, x will be 3 because you're going to subtract 7 from both sides. So one solution is x equals 3. But we also have to consider what happens when x plus 7 is negative 10. Because if we have a negative 10 inside the absolute value, this is negative 10, then you take its absolute value and you get 10. So you also have to consider, when does x plus 7 equal negative 10? And again, we're going to subtract negative 7 from both sides, or subtract positive 7 from both sides, so x will be negative 17. Now you need to check your solution. This is very important in absolute value equations because sometimes they don't actually work, but let's try it. So if x equals 3, we have absolute of 3 plus 7 equals 10, which is absolute 10 equals 10, which absolute value of 10 is 10, so that works. Now let's try x equals negative 17. So I'm going to substitute negative 17 for x. And let's see, negative 17 plus 7, that's negative 10. But I'm inside the absolute value symbol still. So take that absolute value, and you get 10 equals 10. So that works too. So both of these are solutions to that equation. Let's try a more complicated equation with absolute value. This one has multiple steps to it. So the first thing you need to remember if you see something complicated like this is that you always want to isolate your absolute value part of the expression, which is this. So isolate means this has to go and this has to go. So the only thing you see on one side of the equation is the absolute value part, and then on the other side is just numbers or a non-absolute value part of the equation. So first thing we do here is we're going to add 9 to both sides using the addition property of equality. So you get 2 times 3x minus 6 equals negative 3 plus 9. Negative 3 plus 9 is 6. Looks a little better, but it's still not isolated. I still have this 2 hanging out here, so I want to divide both sides by 2 using the division property of equality. And I get this expression, or equation rather. And this time I do have this isolated. So all I have on this side is absolute value, and that's what I want. And now I can use the techniques we talked about in the previous video, which is we need to consider when the expression inside the absolute value is positive. And we also need to consider when is the expression inside the absolute value the negative version of what we're looking for, or negative 3. So we have to solve these two equations. So for the first one, I add 6 to get 9. So x will be 3. And then this one I also add 6, but because I'm adding it to negative 3 plus 6 is 3. This one says x equals 1. Let's do a quick check and make sure it works. So 2 times 3x minus 6, and I think x is 3. That's this one. So minus 6, then minus 9, does that equal negative 3? Well, inside the absolute value, That's 9 minus 6, that's 3. Minus 9, see if that equals negative 3. Absolute value of 3 is just 3, so 3 times 2 is 6, and 6 minus 9 is negative 3, which matches, so this is a good solution. Let's try the solution 1. 2 times 3 times 1 minus 6 minus 9. Is that going to give me negative 3? Well, that's going to be, let's see, 3 times 1 is 3 minus 6 is negative 3. And so the absolute value of negative 3 is positive 3. So that is 6 minus 9. And that's, once again, good solutions here. They both work. And we've solved the equation. This example looks a bit like one we've done before. This is a multi-step case, so as before, you always want to isolate the absolute value part. So to do that for this one, we need to subtract the 10 here from both sides using subtraction property of equality. And we get 2 minus 10, which is negative 8. Now before, what we had done was we said, when does 5x plus 4 equal negative 8? And when does 5x plus 4 equal positive 8, right? Because we want to test both things here. And I can go ahead and do that. But be careful. You're going to write that down. Because you can never be an autopilot when working absolute value. Let's go back to what absolute value means. Absolute value says, how far is some value from 0? So 5x plus 4 represents some numerical value. Now, no matter what that value is, when you take the absolute value of that value, and I'm saying value too many times, think about what should come out of the expression here. Because let's say we did this in the absolute value of this expression, or the actual value of the expression, say 2. So the absolute value of 2, well, wait a minute. And then what if this came out to be negative 2? The absolute value of negative 2 is not negative 8. In fact, anytime we put an expression inside absolute value, I think the smallest value it can ever be is 0, because anything else will be a distance from 0. Distance is always a positive number. We can never get a negative value when you're taking absolute value. So there is no solution to this absolute value equation. So be super careful and always think before you just progress. Here's another absolute value equation. This one has x on both sides, and we haven't seen that before. Absolute value equations can not only have x's on both sides, you can have absolute value on both sides. You just have to be super careful with these. As always, you want isolation of an absolute value expression on one side, which is what we have here. And then you say, well, what happens if the value inside is positive? What happens when the value inside is negative? So it really is following the same rules as before. So first we want to say, well, what happens when x, the value inside the absolute value, exactly equals the value outside the absolute value on the other side of the equation. And the other thing you want to check is what happens if x is the negative of the value to the right of the equation. This one here, that is not an absolute value. These are the two equations we want to solve. So let's see. The first one, we're going to add this negative x. I'm going to add the negative x to this side of the equation. So I'm going to get 2x equals 6, x equals 3. Okay, easy enough. Let's look at the other side. Now I've got a negative here, so I want to distribute it. Negative times negative x, that's positive x. And negative times plus 6, that's minus 6. So let's see. To solve this, I want x on one side, so I'm going to subtract this x here. But when I do that, I get this strange thing here. I get 0 equals negative 6, which is a false statement. So what math is trying to tell me here is that I can't find another solution. It's making no sense. There is no solution that will give me an opposite value that will make this equation work. So apparently x equals 3 is the only one. As always, check it out and make sure. Because even sometimes when you get a sensical solution, when you plug it in, it doesn't work. So you always, always, always check. So let's see. Wherever I see an x, I'm going to put a 3 in, because that's what I believe my solution is. So there was an x here, there was an x there. The absolute value of 3 is 3. And then when I combine those terms there, I get 3 equals 3. So that works. There is only one solution in this particular case. Always check. Even if you get something you might have gotten in other examples, other equations, you could get 2 x's, but one of them will not work when you do the check. So always, always check the solutions that come up. For this example, I'm going to show you how to solve an absolute value equation using graphing. Graphing method is a very helpful way to see why we sometimes get no solution when we are trying to graph things. So basically what you do is you're going to graph this side, and then you're going to graph this side. That is, you're going to graph y equals x minus 2 in absolute value, and also y equals 3. And then you're going to look to see when are these two graphs equal? And you know graphs are equal when they intersect. So let's graph both these things. Now, a couple of ways that I can think of to graph y equals absolute x minus 2. One way to use an xy table, and that involves selecting members of the domain and then plugging them in and getting y values and plotting them. So go ahead and do that if that's what you know how to do. If you are familiar with graphing with transformations, we can do that here. X minus 2, that means you're subtracting 2 from an input. That's when we would take the graph of y equals absolute x, the parent function of this guy, and we would shift it right 2. So if you don't know how to do that, that's okay. That's a topic for another video. But for those of you that do, basically all you do is instead of graphing y equals x, which would be over here, we're going to shift that graph 2 over so that it's over here. So let's go ahead and do that. So instead of being at the origin 0, 0, I'm shifting the vertex of y equals absolute x to the right 2. And then I'm basically graphing y equals absolute x, but from this position. So a little bit shaky, these lines here. But that is a very rough estimate of what y equals absolute x minus 2 looks like. To graph y equals 3, I just want to show on the graph every point that has a y value of 3, and that will be the horizontal line over here. Now I'm looking at this graph here. It's not very good. Just trying to correct the sloppiness, though maybe I'm making it more sloppy. But anyway, so I've graphed both these things, and so I want to figure out where is the intersection. So the intersection of that will be one over here and one over here. And let's see, 1, 2, 3, 4, 5, right? That's at x equals 5, and this is at x equals negative 1. Now, if you want to verify that, let's try to solve this one algebraically. And the way you do that is you say, when does x minus 2 equal 3? And then when does x minus 2 equal negative 3? If you solve both of these, we get the same result. It's just, we're just checking kind of what we did. So we can see where the solutions are. And then just real quick, how come sometimes we get no solution? So graphing can help us. If you have the equation absolute x plus 5 equals 1, I don't know what this is, absolute value of x plus 5 equals 1, if you were to graph that, the absolute value of x plus 5, again, using transformations, I know that this means take the graph of y equals absolute x, take this graph and shift it up 5 units. So just a quick sketch, you would have something like that right over here, and that's at 5. And then what does x equal 1 look like? X equal 1 looks like this. And these are two graphs that will never intersect, so there will be no solution. And algebraically, when you subtract that 5, you would get x equals -4. So we understand that the absolute value of x will never be -4. But I sometimes think just looking at the picture of it, it really gives us an idea of why sometimes things will work, sometimes they will not be solutions. So it's just a nice handy little thing to do, especially if you have a graphing calculator. You can always just pop in either side of the equation as two different y equals two different graphs and just look. So hope that was an interesting and somewhat helpful way to look at graphing and solving absolute value equations.